data kaydet. Okay. Let's do part 3. So sorry, V of f y plus f times covariant derivative. Let's see why this is true. So Vy, of course. So this expression is just what? This is d dt of inside
Hocam,
this.
tahta yine kaldı da.
Aslında tahta olduğu yerde de sanırım şey, bu donmuş, pardon. Okay. So we are trying to prove the third part of the theorem. So what is this? It is just this expression. So we take the derivative of this at t equals 0. Now what is this? This is d dt of, now inside f I put this gadget and times y p plus tv and take the derivative at t equals 0. See here I have two expressions, a function times another function, right? These are two functions. One of them is scalar valid, the other one is vector valid, but product of two functions and I take derivative. Well, we use Leibniz rule. Derivative of the first guy, so d dt of f of p plus tv at t equals 0 times this object at t equals 0. So p plus 0 times v plus the first object evaluated at t equals 0 times derivative of this d dt of y p plus tv at t equals 0. All right. Well, let me write here what these are. What is this? This is the directional derivative of f at the point P along the vector V, right? So this is just directional derivative of f along the vector V. And what is this? This is just y of P. And what is this? This is f of P. And what is this? Well, this is just the covariant derivative of y along the vector V. Okay. So we are done, right? So we obtain exactly this expression. The fourth part is similar. So let me write here. Part 2 and 4 of the theorem are left as an exercise. If you don't understand what's going on, just write down everything in detail, then it will be clear, okay? We are just taking derivative, basically. Efendim? Yeah, so you just take derivatives. But you see, taking derivative is getting more and more complicated, right? You are taking derivative, but its name is keep changing. All right. Kusura bakmayın. Okay. Ne yaptığımı da unutuyorum. 54, 55. Okay. Did it change to board one? No. Okay, now let's write down a corollary for this. Yeah. Okay, let me write. The same result holds if we replace the vectors v and w at p by vector fields. V and W on R3. So what we claim is that the same theorem holds if I replace these two vectors, right? In the theorem, in this theorem, V and W were just two vectors at a point. But, you know, if you look at the proofs, you see that this holds for every point, and you are not taking derivative of these gadgets, right? You are not taking derivative of V or W. Therefore, I can just assume that these are not just vectors, actually, but vector fields, okay? And I just keep doing the same thing at each point, okay? So the statement is the following. The proof is the same. Statement is a little bit different. Corollary. Tahta döndü değil mi? Tamam. Let V, W, Y, and Z be vector fields. Be vector fields on R3 F and G functions on R3 and AB are just constants. Then we have the same statements. So let me rewrite them. The first one is, so I have A times the vector field V, B times the vector field V along of the vector field Y. Okay. Yani aslında şöyle diyeyim, bu one prime, şu A ile B yerine bunları fonksiyon da alabilirdik. Şöyle yazayım. So this is f times this plus g times this. You see, at any point, f and g are just two constants. Therefore, these two statements are basically the same. This is just the parametric version of this, right? This is at a single point, this at any point. And as you change the point, these coefficients A and B might change, so I can take them as some functions. The second one is this. Here these are constants, A times B, Y plus B times VZ. We proved this one, right? Bunu mu ispat etmiştik? Yok. Onu ispat etmek. Bu kolay olan. We have this. VF Y plus F. Okay. And okay. No, F and G doesn't go out because you are taking derivative here, right? You have to use this. Summation is okay, but if you have a function in front, then you have to have this. So let me write down what you have said. So your friend asked this. So let me write remark. What if I have here not constants but functions, let's say f and g, what would be the result? Well, summation will split because derivative of a sum is the sum of the derivatives, but derivative of a product is not this, right? You have to use Leibniz rule. So I should write it this way. Covariant derivative of f times y plus g times z, let's say, this can be written like this. No problem with that. It splits like this. And then you use part 3. Part 3 tells us what? You have to take derivative of f, which is this, times y plus f times derivative of y. And same thing here. Derivative of g times z plus g times derivative of z. Okay.
Hocam tahta yine mi dondu yoksa benim mi öyle?
Donmuş. Evet, pardon. Bu bir de öyle bir şey var. Özür dilerim. So your friend asked if I can take just this constant, these functions out as if they are constants here. Well, you can't do that because f and g are functions and you are taking derivative. But the thing you can do, you can split this into two parts, since it is the derivative of a sum, which is equal to sum of the derivatives. But then when taking these functions out, you have to use Leibniz rule. And this is the actually expression you would get. All right, so do I need this stuff? Let me see. No, I don't need, I guess. We already seen what's the frame field, right? So, okay, if I need, I will come back to this, but all right, let's go back to shape operator. Neyse tahtayı sileyim, ondan sonra değiştireyim. So, back to the shape operator. Okay, now let Z be a Euclidean vector field. Just a vector field on a surface M. So here, of course, what we mean by that is the following. No, okay, let me continue. Let P be a point in M and V a tangent vector to M at the point M. Okay. Then we define the covariant derivative of Z at P along V as this expression. I will compare with our previous covariant derivative definition. So Z of alpha, derivative of this evaluated at 0, where alpha is a curve, is any curve on M, so that alpha 0 is equal to P and alpha prime is equal to V. Well, this derivative, covariant derivative, looks a little bit different than we have just defined in the last hour. But let's see that they are actually the same thing, okay? And I will also tell you why we need something like this, you know, since we had already one definition. So why do we have to give a new definition. Well, let me, recall that for a vector field y on R3, the covariant derivative along a vector v TP-R3, değil mi? R3'ün bir teğet vektörü için nasıl tarif edilmişti? Is defined as, şöyle tarif edilmişti. Özür dilerim. ddt of y p plus tv, değil mi? T equals 0. Şimdi bu neydi? So here I am at this point and I have this vector v, and I just actually move on this line, right? As t changes. So this point, what is this point? This point is just, so if this is my vector v, this point is just p plus tv. And I put that gadget inside. But actually, I can put any other curve here. This is a curve, but a special curve. It is just a line. And I don't have to take any other curve. Why is that? Because I am in R3, and this line lies in R3. So I can just use this gadget to define the covariant derivative. But I could do the following. If I have just any other curve, alpha, so that alpha at 0 is equal to p and alpha prime is equal to v, this thing is just equal to ddt of y of alpha t at t equals 0. Okay, instead of this line, I could use any curve, because when you take derivative of this, you will see that you get the same thing, right? It doesn't matter which curve you choose. The only thing you need is that this curve should pass through this point at the time equals 0, and it should have velocity vector v. Okay. Peki niye böyle tarif etmedik? Why we didn't define it this way then? Well, we didn't need, to define it this way, because this is simpler and it works in our case. However, if you are on a surface like this, some surface, then, and suppose you are at this point P, and you have a tangent vector V, then the line segment P plus TV, what is this line? It is this line. This line doesn't belong to the surface, right? This line, the point of this line is not contained in the surface. Değil mi? Yani aynı şeyi yapmaya kalksaydınız, noktayı vektör boyunca, doğru boyunca iterseniz, surface'ı o bir noktada delip geçecek. Surface'ın üzerinde kalmıyor. R3'ün içinde kaldığı için bunu böyle tarif edebilirim, ama surface'ın içinde kalmıyor bu. O zaman ne yapıyorum? Diyorum ki line almayacağım. Line yerine surface'ın içinde kalan bir eğri alacağım. Ve şunu biliyorum ki surface'ın içinde kalan bir eğri aldığın zaman, yani hangi eğriyi alırsan al, zaten bu ikisi aynı şey. Yani bu tanıma bir zarar gelmiyor. Yani R3 için bunu kullanabilirim ama aslında buraya herhangi bir eğri de koyabilirim. Ama bu avantajlı benim için. Neden? Çünkü Surface üzerinde türev alacaksam doğrular işimi görmüyor. Eğriler almak zorundayım. So, if you are in R3, it doesn't matter which curve you choose to take the derivative, right? I can choose line or any other curve. But on the surface, you know, I need to stay on the surface. Why is that? Because you see, this vector field is defined on the surface. So if you move off the surface, then this is no longer defined. So I cannot make use of this gadget. So I cannot just do this ddt of what? Zp plus tv, right, at t equals 0. The thing is that for t values different than 0, this point is not on the surface. Therefore, z of that point is not defined. Z is defined on the surface now. Okay, so this definition doesn't work. That's why you have to choose a path which lies on your surface. Okay, sure. You mean why didn't we start with that definition? Yeah. Vector field on M, or yeah, but the thing is that we may have a vector field which is only defined on the surface M. Maybe it is not defined on M, on R3. Okay, and this way, this is actually more advantageous. You know, this thing, this definition works on M, and it is kind of independent how it is embedded into R3, because you know everything happens inside M. But the other definition use the fact that your surface lies in R3 and so on. Okay. Okay. So to define the covariant vector field, we just need to choose a path on the surface M. Okay, that's it. All right. Here is a lemma. Let Z, which has this form, I from 1 to 3, be a vector field on a surface M. Then for any vector we have, well, of course, this is just, we proved actually last hour for vector fields in R3, right? But let's prove it again. Okay, so what is the definition? Well, suppose this is our source M. I am at a point P, and I would like to take of a given vector field along a vector V. Vector V. By the definition, first I need to choose some path which passes through that point and has velocity vector V. So choose sub alpha with alpha 0 equals P and alpha prime 0 equals V. Then what is this gadget? Well, this is just d dt of z of alpha t, right? At t equals 0. What is z of alpha? Okay, so d dt of z of alpha. So z is this. Inside this, I put alpha t. This is a constant vector field. Alpha t just goes inside this coefficient function. So z of alpha is just this. I from 1 up to 3, zi. So this is the function. And inside this function, I put alpha t times the constant vector field u. Right? These are the unit vector fields like 1, 0, 0, 0, 1, 0, and 0, 0, 1. Right? U1, U2, U3. The variable part is this coefficient function. Okay. What is the derivative of this? Well, this is constant, right? This is just a function, constant vector. You multiply this with a function and then you take derivative. You will take derivative term-wise. So this is just I from 1 up to 3. Derivative of this expression, d dt of zi alpha t at t equals 0 and then ui. Okay, what is this derivative? Right here, I have to take this derivative. Okay, what is this derivative? I have a function, right? Zi is a function from, it's a function on M into R. I take derivative. Okay. I may consider this function defined on what? Actually, you see there's a surface patch here, right? There's a surface patch, and then we had this X here. locally I can just consider it as a function defined on this surface patch. If I come down by the inverse of the surface patch, then I have this function. So I go by x inverse and then by z. So I can consider it as a function on R2, and you take derivative of this. That will be just evet, x doğru, haklısın, x olacak. Okay. So what is this derivative? Yeah, since this is the curve with the following property, alpha 0 is equal to P and alpha prime 0 is equal to V. So this thing is just V of Zi, right, times Ui. Yani Zi fonksiyonunun V boyuncaki türevini alıyorsunuz. O da zaten bizim yapmak istediğimiz şey. Değil mi? Şu ifade nedir? Zi fonksiyonunun V boyunca türevini almak. Hangi noktada? P noktasında. Yani o da zaten işte V vektörü. Evet. You can using this notation, but actually you don't need it. Okay. Burada tabii şunu da görmüş olduk. Let me write here as a remark. You see, here I don't have any alpha, and here I don't have any alpha, but to define this, I need alpha, right? There is alpha here, but this proof shows that actually it is independent of the alpha. The only thing we use about alpha is that it passes through the point P, and at 0, its vector is V. Therefore, defining this derivative using this auxiliary curve alpha is, legitimate. So this is a well-defined object. It doesn't depend on the choice of the curve alpha. Okay, so this proof also shows that the definition of this covariant derivative is independent of the choice of the curve alpha, as long as it passes through the point P with the velocity vector V at 0. Yani bir nesneyi tarif etmek için bir takım seçimlerde bulunuyoruz ama sonuç o seçimlerden bağımsız. O zaman bu, değil mi, iyi tanımlı bir nesne oluyor. Alfaya göre değişseydi o zaman benim alfayı buraya koymam gerekirdi. Ama alfadan bağımsız, sadece V'ye bağlı. O yüzden bu iyi tanımlı bir şey. And this is a well-defined object. Okay. Let me give a final definition, and then I will stop. a surface M is called orientable if there is a continuous function u from the surface into R3 so that it is never zero and it is always perpendicular to the tangent plane. Okay, for OP. Well, perpendicular to the tangent plane means, of course, this, right? In other words, UP times V is equal to 0 for all V in TPM, right? Perpendicular to a plane means it is perpendicular to all the vectors in that plane. Okay. Example, we have seen that if your surface is a level surface of a function, then its gradient, right? UP is a normal vector, so that right, this is never zero, and it is perpendicular all the tangent vectors. This is perpendicular to tangent vectors. Therefore, this is orientable. Okay, orientable. So any level surface is orientable. In particular, sphere is orientable. Right? At each point, you have a normal vector, like this. It is perpendicular to the surface at each point. Perpendicular to the tangent plane. Bu şöyle mi olur? Şöyle olur, değil mi? Non-orientable surface. Okay. That's exactly what I would do. Okay, here's this surface. You can do this at home. Take a piece of paper like this, a rectangular paper, and then just glue back these two edges as shown by this arrow. So you make a twist and then glue back to the other end. So suppose this is the end A. So A is this. So you twist one of the ends 180 degrees and glue back to the other end. Okay, you get so-called, you know the name of this, right? This is Möbius band. This is non-orientable. It is non-orientable. Proof is not that easy, but you know, you can see why it is not orientable. Suppose it is orientable, then there should be a vector field which is perpendicular to surface at all points, and that vector field should be what? Should be continuous. Well, at this point, if it is perpendicular, then it should be like this, right? Outside, it should point like outside the board, right? Like this. And as you move, right, that vector, what? It goes like this, right? It bends like this. So that vector will go like this. Değil mi? Şöyle yukarıya doğru gidiyor. Burada da şöyle. Ama burada şöyle döndürüyorsunuz. Artık arkaya bakıyor. Yani şöyle düşünün. Right? It has this vector field at all points. It points towards you. Then I make a twist 180 degrees and I glue back here. Okay? That vector point time inside the board, and the function will be not continuous because here it is pointing this way, this way, this way, and when you come here, it suddenly goes the other way, right? The opposite way. That function is not continuous because I identified this point and this point. So it should take the same value. But here, if it's pointing this way, this point, it's pointing exactly the opposite way. Therefore, that function cannot be continuous. That's basically the proof. But there are rigorous ways of proving this. Okay. Yeah, exactly. But showing that it may not be, that easy. It's a little bit tricky. Not difficult, but a little bit tricky. Okay. Yeah, if you don't connect them, it's okay. But when you connect it, yeah, anything that contains a copy of Möbius band is not orientable. Klein bottle is not orientable. RP2 is not orientable. Well, real projective plane. The Euclidean, not the Euclidean plane, but the projective plane, where you do projective geometry. Okay, let me stop.